All right, well, welcome everyone to the Peale lecture. Most of the faces here are young enough or recent enough additions to the department that you never had the pleasure of meeting Professor Stan Peale, who left a legacy, particularly in the sense, I think, that he was the first astrophysicist here in the physics department. And if I understand correctly, somewhat by chance, he was at UCLA and the air down there got to him, the pollution and stuff, and somehow managed to transfer up here. And it was so he's our founding member in some sense. But besides being a brilliant dynamicist and planetary scientist, Stan was just a tremendously wonderful colleague in every way. You know, the sort of person that you'd meet at tea every day and discuss something fabulous. So we miss him dearly, and to his legacy, it's been almost 11 years now since he passed away. We started something called the Peale Lecture, that those of you who do remember him, we thank many of you for contributing to funding and endowing that lecture, which enables us to bring someone from some distance in to give a colloquium yearly. And this year, it's particularly fitting that our speaker is Hoi Lee from the University of Hong Kong. He was a postdoc here in the department with Stan. Got his undergraduate degree at the University of Toronto, and then was a Princeton PhD student. And is very much following in Stan's steps in terms of his topics in planetary dynamics. And I'm gonna give the floor to him. He's gonna tell us today about the dynamics and origins of mean motion resonances in extrasolar planetary systems. And I know I'm going to learn a lot from this because I really have no idea what that means. So, the floor is yours, Hoi.
All right, thank you. Okay, thank you, Crystal. It's a great honor for me to be giving this lecture named after Stan, and also very meaningful for me because he was a very important mentor for me during the time when I was here and also actually subsequently. When I came here, I actually didn't really know that I would be actually one of only very few people that were postdocs with Stan. So actually back in 2006, we took this picture in the DPS meeting in Pasadena, and there was one more postdoc after me, but this was the whole group. So there were only 4 or 5 postdocs in total throughout his career. Some of you may recognize some of the people here. So this is actually Jack Wisdom, Jack Lissauer, and Dave Carey, and then me. So this was back in 2006, and there has been, the total number of postdocs that Stan had was 5. I moved back to Hong Kong in about, at the beginning of 2008. So actually in 2007, I guess after I got the offer from Hong Kong, we actually went to Los Angeles for a celebration, so this was a picture taken at that time. When I moved back to Hong Kong, we started some work about the satellite systems of Pluto-Charon, maybe 2005, 2006, and we were still talking about, or thinking about doing some more work on that topic. So actually I was very happy to actually be able to convince Stan to go to Hong Kong in 2010. At that time, my student was working on the problem about the satellites of Pluto-Charon, and that eventually resulted in 2 papers, which I think were not quite the last papers that Stan wrote, but close to being one of the last ones that he co-authored. And even now, actually, I'm still working on the problem about the satellites of Pluto-Charon because it's still a bit of a mystery to me, at least. Stan, for those of you who didn't know, he was actually very well known as a dynamicist who did a lot of pioneering work about the dynamics of solar system bodies. particularly about resonances and also rotational states, tidal evolution, etc. But maybe less well known is the fact that he was also a real pioneer in study of exoplanets. Most of you, when we talk about exoplanets, we usually talk about the discovery of 51 Pegasi b in 1995 as the first planet around a sun-like star that was discovered outside the solar system. But some of you may also know that actually a couple of years, or 3 years before that, actually the first set of exoplanets were actually discovered around pulsars, which is really weird. And he actually wrote one of the major papers that, because that system actually turned out to show signal for 2 planets going around the pulsar, which is also weird. And he wrote a paper showing that because these 2 planets are actually near a mean motion resonance, there should be detectable dynamical effects. And that was what was detected from the pulsar signals, and that's how it was proven that in fact this really was a planetary system around the pulsar. He was also, he got really interested in using one of the method called microgravitational microlensing to find exoplanets. He actually wrote quite a whole series of papers talking about how what could one expect to find through microlensing survey in terms of the rate of finding exoplanets around stars. You would be happy to know that actually this has now become a very successful method. Many planets have been discovered that way, including, really interestingly, we now have evidence for free-floating planets from gravitational microlensing. Now, where the story for this talk came in was around 2001 or 2000, when I was here as a postdoc with him. We were actually working on a problem on the satellites of Saturn. But this system came up, GJ 76, and immediately I remember Stan telling me that there was something unusual about the configuration of this satellite system because he was, of course, really well. He knew very well the resonances in the Galilean satellites for Jupiter. And as you will see, it's kind of a similar sort of thing, but it turns out to be in a different configuration. So that's how we got started in thinking about this problem and published a paper in 2002, which was my first paper on exoplanet and kind of got me into this, as you will see, kind of this series of work that I've been working on mean motion resonances in exoplanets. Now, I assume not everyone here works in exoplanets, so I'll first spend a few minutes telling you some basic things about exoplanets before I move on to mean motion resonances. So up to now, so as I said, in terms of the solar type stars, the first one was discovered in 1995, and up to now, the field has really exploded, and we now have something like over 6,000 confirmed exosolar planets. For dynamicists, one of the interesting category are systems that have multiple planets detected, 2 or more, and we now have over 1,000 of these. Most of the planets have been discovered by either transit or radial velocity, but as I mentioned, microlensing is now a very successful method, and also a few, still only a few systems have been discovered by direct imaging. So I'll say a little bit about the 2 main methods, radial velocity method and transit. So for radial velocity method, the idea is that the planet is very faint. You can't easily detect the direct light from the planet, but you can easily monitor the spectrum of light coming from the star. If you have a planet going around the star, then actually, strictly speaking, it's both of them moving around the center of mass of the 2 bodies. And so the star, repeat, is moving back and forth around the center of mass. And so when if that star is moving towards you, then you should see the spectral line shifted to the blue. And if it's moving away from you, the spectral line will be shifted to the red. And so if you monitor this over time and see a periodic shifting back and forth in velocity, then you can confirm that there's actually a planet around that star. And the signal might look something like this, right? So there are a few main properties. You have obviously the period of that signal, the overall amplitude, and the shape of the radial velocity curve. From the shape, you can deduce properties like the eccentricity of the orbit. period, if you know the stellar mass, then you can use Kepler's third law to convert that into semi-major axis of the orbit of the planet. And then from the amplitude, you can use that to derive the minimum mass of the planet. One of the problems about the radial velocity method is that there's a degeneracy that we don't know the inclination of the orbit of the planet because different inclination give you exactly the same signal. And so the only way you can break that degeneracy is, at least one of the ways, is if you actually have multiple planets in that system and the planets interact sufficiently that you can see the effects of that interaction on the radial velocity curve. If that's the case, then you can actually break the degeneracy in sin line. So this was the radial velocity method, was that method by which that first exoplanet around the Sun-like star was discovered back in 1995, just over 30 years ago. And this was discovered around the star 51 Pegasi. This is kind of the radial velocity signal that was detected for that particular planet. From the amplitude, again, you can deduce that the minimum mass of the planet is around half the Jupiter mass. So that's not unusual. It's a kind of a Saturn-type planet. But what was very unusual was the fact that the period is only 4 days. And so that's if you know your solar system planets, right? Our own Jupiter goes around every 11, 12 years, and Mercury is every 88 days. And so this is a planet that goes around its parent star every 4 days, and it's about the mass of Jupiter. So it's a very large planet that is very, very close to the star. And so this is now in the category of planet which are referred to as hot Jupiters. For the other very successful method, which is transit, conceptually is relatively easy. If you have a planet going around the star and if the orbital plane happens to be more or less along the line of sight of the observer, then every time that the planet goes around, there will be a few hours typically when it's going in front of the star and blocking out some of the light from the star. And so then if you continuously monitor the brightness of the star with sufficient accuracy, you will see that over a few hours it will dim by something like 1% if you're talking about a Jupiter-sized planet going in front of the sun. The challenge is if you want to detect the transit from a much smaller planet, like an Earth-sized planet in front of the sun, then you need accuracy of something like 1 part in 10,000 to be able to do that. And the other challenge is, again, that it only works if the orbit of the planet happens to be nearly edge-on from the observer. And so that means is that if you have random orbit orientation, most of the planets that are out there, you won't be able to detect by this method. And also that means that you need to monitor a large number of stars in order to actually discover planets by this method. So that turns out to be the method by which the famous Kepler Space Telescope was using, and it was designed to be able to detect Earth-sized planet going in front of a sun-like star. And so it was extremely successful, and also the currently operating successor called TESS. Both of these are using the the transit method to detect planets. And they have now, so out of that 6,000 planets, a large majority was discovered by Kepler plus TESS. So there you can see here that it clearly actually successfully detected Earth-sized planets, lots of Neptune-sized planets, Jovian-sized planets, but we also know from, particularly also from Kepler observations, starting with Kepler observations, that there's a category, actually there are 2 categories of planets that we don't have in the solar system. So these are now referred to as the super-Earths and the sub-Neptunes, which have sizes in between the Earth-sized planets and Uranus and Neptune in our own solar system. So by now, as I said, we now have something like 6,000 planets. And you can look at some of the overall statistical properties of the type of planets that we have been finding. So this is a plot showing you the mass or minimum mass in units of Jupiter mass versus the orbital periods of the planets. And also plotted here are the planets in our own solar system. Down here, this kind of lower right corner, we actually haven't detected any planets only because selection effects, limitations of the observation techniques that we can't really find planets down here yet. So you see lots and lots of planets. So I mentioned that there are these hot Jupiters of older Jupiter mass that have very short orbital period. And it's not just Jupiter-sized planets. You obviously also see Earth-sized and super-Earth, sub-Neptunes down at very short period. And the shortest period now, amazingly, is something like less than half a day, which is really mind-boggling. You also see some patterns, which I don't have time to talk about, like the fact that there are these things that are called warm Jupiter with orbits of tens of days, but they are relatively rare compared to the hot Jupiter and the cold Jupiters. The other overall property you might be interested in would be the orbital eccentricity of the orbit versus the orbital period. So eccentricity is a number that goes from 0 if the orbit is circular up to 1, which would be the most elliptical orbit or bound orbit. And for the short orbital period, there are lots of planets that have very, basically 0 or very low eccentricity, and that is due to the effects of tides, tidal dissipation, circularizing the orbits. And that's also a topic that's then worked on quite a bit in our own solar system. What's also really that interesting is that beyond, say, 10 days, you see actually a very large distribution of eccentricity, unlike the solar system planets, which are nearly circular. And actually there are eccentricity going all the way up beyond 0.9. And so there's a lot of study trying to figure out how you actually generate these very high eccentricities, most likely through dynamical processes. So by now, as you saw there are a number of interesting things overall that we have discovered. Right? We have Jupiter-sized planets and all the other sized planets, which are very close to the stars. And as you just saw, there are planets that have very wide range of orbital eccentricities, going all the way up to beyond 0.8. Something that I don't have time to talk about is that we have also now found planets in a number of unusual contexts. Other than just focusing on sun-like stars, there have been surveys trying to find planets around both lower mass stars and higher mass stars, and we have found those, but with different statistics compared to, say, sun-like stars. A topic that I've been really interested in the last few years is actually planets in binary star systems. And in binary star systems, you can have planets which are going around one of the stars in the binary, or it can be going around the binary. And we have discovered both types of planets. And that's a topic that, again, I don't have time to talk about here, but if you're interested, you can certainly ask me about that. And then specifically for the topic today is the fact that we have discovered planets which are multi-planet system with 2 or more planets, with the planets either actually in mean motion resonances or close to mean motion resonances. So that's the focus of the topic for today. So let me first say a little bit about mean motion resonances. Most of you wouldn't be familiar with the term mean motion resonances. In the simplest explanation, we are talking about situations where the orbital periods are near some simple integer ratios, like 2 to 1 or 3 to 2. But as I will explain later, that's kind of just qualitatively explaining what it is, but in more detailed way, there are specific requirements that has to be satisfied. So in our own solar system, there are lots and lots of examples of mean motion resonances among the minor bodies or the satellite system in the solar system. So well-known examples like the Pluto, which is actually in a 3 to 2 resonance with Neptune. So what that means is that every 2 times that Pluto goes around the Sun, Neptune goes around about 3 times. And in fact, Pluto's orbit is so eccentric that it intersects the orbit of Neptune, and the fact that they don't crash into each other is because of this resonance. The other famous one, again, there are lots of examples of resonances in the satellite system. One of the famous one is what's called the Laplace resonance for the Galilean satellites around Jupiter. So these are Io, Europa, and Ganymede. And the period ratio is now 1 to 2 to 4. And this is an illustration of that resonance between these 3 satellites. The dash here indicates what I call the periastron, or in this case peridrome. So the location in the elliptical orbit where the satellite is closest to Jupiter. And you can see here that in the Laplace resonance for the Io and Europa, the orbits are actually anti-aligned. So the peridrove of Io is over here, while the peridrove of Europa is over there. And in fact, it is this resonance which led to one of the results that Stan was most famous for, is the fact that there is this resonance which make the orbits non-circular, and then you can then calculate how much tidal dissipation is happening inside the satellites, and then you will, as Stan worked out, that it turns out that the amount of heat being input into Io is so large that the entire Io should be melted, and so they actually famously wrote a paper, I think a few weeks before the first Voyager and close to flyby, that Io should be volcanically active from this analysis, and that's what was found when Voyager first took a picture of Io. Interestingly, so there are all these examples of resonances in our own solar system, but interestingly, there are no mean motion resonances among the planets in our own solar system. Something I guess I won't talk about here. We now think that maybe at some point very early on, the solar system might in fact have the planets in resonances, but then that eventually there was some sort of instability, and then there was some dynamical instability going on, and eventually the planets ended up with the orbits that we see now. So there is still possible that in fact very early on, our own solar system actually have planets in mean motion resonances. Now, so the story, so that was again, what we know from our own solar system. And then in 2001, it was announced that a system called around the star GJ76 was discovered with two planets that look like they're in 2-to-1 resonance. And so this is the radial velocity signal from around that time. So that by that time there was already something like at least 8-9 years of data. And these two Jupiter-sized planets have orbital periods of about 30 days and 60 days. And when we worked on this when I worked on this with Stan, this is, and I'll talk about this in more detail, this is actually the configuration these two planets have. Again, the dash shows where the periastron, the closest distant star is. And you will notice here that in fact they're aligned with each other, unlike the Io Europa case where they're anti-aligned. And so that was, as I said, that was kind of the, what I remember Stan telling me something is weird going on here, right? Because the configuration is not what you expect from what we know from the Io Europa configuration. Subsequently, after a few more years, we now know that there are at least 2 more planets in that system. And at least one of these planets is actually in resonance with these other 2. And in fact, they now form a Laplace resonance, as I'll also tell you a bit later. So, so other than having a pair of planets in resonance, so this is now also the first example, this system became the first example of what's called 3-body resonance involving 3 planets. And there are now actually many other examples of these multi-planet resonant chains, which is now turned out to be very interesting also dynamically, and also what they tell us about the formation of planets. So subsequently, since this GJ76 system, there has been many more examples of mean motion resonances and also resonant chains. So I just listed a few of these. Examples of 2-to-1 resonance around sun-like stars and also around giant stars, 4-to-3 resonance. The first resonant chain, I think, was this one, Kepler 60. But other than GJ76, the first resonant chain found by Kepler, I should say, was Kepler 60, which has 3 planets with period ratio of 5 to 4 to 3. Okay, so that means that, that one pair has a ratio of 5 to 4, the other one has 4 to 3. There is this one with 4 planets around Kepler 223, and then Kepler 80, which has 6 planets at least 5 of the planets are in a resonant chain with period ratios of 9 to 6 to 4 to 3 to 2. And one of the most well-known ones that many of you have heard of, at least as a planetary system, is actually TRAPPIST-1. So it was famous because it has a total of 7 planets, which are all Earth-sized. And also, really weirdly, it's going around a very, very low mass M dwarf of only about 8% of the mass of the Sun. So this system made quite a bit of news when it was discovered. But also, very interestingly, even in this system, at least 5 of the 7 planets, the outer 5, are actually in a resonant chain. So if you take the orbital periods and take the ratio of the adjacent planets, you will find that the ratios are 3 to 2, 3 to 2, 4 to 3, and 3 to 2. The inner 2 planets are probably only close to but not actually in the resonance. So you will notice a couple of things. One is that most of the examples I mentioned involve integer ratios which are with the integer number only offset by 1. So 2 to 1, 3 to 2, 4 to 3, etc. There are some examples of higher order resonances, and I'll mention some of those later. The reason why first order resonance, so these are what I call first order resonances, when the 2 numbers differ in the ratio differ by only 1. And these so-called first order resonances are dynamically, if you work out the properties of the different resonances, you will find that the first order resonances are in fact the strongest resonances. And so it's not surprising that most of the observed systems are in fact trapped in these, if they're trapped, then they would be trapped most likely in the first order resonances. Later on, again starting with Kepler, and now with more data, one of the interesting results that have been discovered is that there are actually excesses of planets with, if you look at all the multi-planet systems, and take the period ratios, you'll find that actually there's an excess of planet pairs with period ratios which are just slightly higher than the simple integer ratio like 2 to 1 and 3 to 2. So you can see kind of an excess here and also an excess here just outside the period ratio. There's actually a well-known deficit also just inside, particularly for 2 to 1. And so there's been, and this has been updated with different analysis in the last couple of years. And so there's a lot of interesting questions about how you form the resonances. Some of these pairs are actually, we know that they're near resonances, but actually not in resonances. So then there's also the question of like, why are they there? So there are lots of interesting questions. Also, even just the fact that not all the planets are trapped in resonances is an interesting question, as I'll tell you how we think they form. And the scenario, the mechanism seem like something generic enough that you should expect even more planets that are in mean-motion resonances, but they're not. Okay, so let me spend a few minutes talking about the actual, in a little bit more detail about the dynamics of the mean-motion resonances. As I said, the simple explanation is the fact that the period of the 2 orbital periods have a simple integer ratio like 2 to 1 and 3 to 2 or even 3 to 1. But more rigorously, you cannot just say that the ratio is close to that number. You actually have to look at these things that are called resonant angles to figure out if the pairs is actually in a resonance or not. And so if you have say a K order resonance, so let's say we limit ourselves to first order resonances actually to 1 and 3 to 2, then there are actually 2 resonant angles in the classical formalism that you need to look at. So I won't bore you with the details here. I think I've been noticing to example later. But the lambdas here are what I call the mean longitudes of the planet. That tells you where the planets are on its orbit. And the omega 1 and omega 2 are actually telling you the orientation of where the periastron or periapse of the orbit is in 3-dimensional space, in 2-dimensional space. And so this actually tells you something about how the orbits are aligned or misaligned from each other. So in order for you to say that a planet is actually, a pair of planets are actually in a mean motion resonance, It's not just saying that the orbital period ratios are near an integral ratio, but you have to show that actually these resonant angles, at least one of these resonant angles, should be oscillating rather than circulating. And the analogy, which is useful here, is actually it's kind of like a pendulum problem. So when you have resonance, then it's like the pendulum swinging back and forth, and the circulation is when the angle is doing this. Okay? And also very good with this analogy is that in the pendulum problem, you might remember that there's actually a separatrix separating the oscillating motion with the circulating motion, because the separatrix is when the pendulum is upside down, which has infinite period. Okay, so it's actually there's a very good analogy between this problem and the pendulum problem. Now, I remember when I was first working on this problem, it's actually not very obvious how a lot of this analysis was done in solar system problem for what's called a restricted free body problem, so that you can assume that one of the planetary body has basically no mass. And so it wasn't obvious how you actually generalize this to a two-planet problem where both planets are massive. And so this has finally been done in the last, I guess it's now almost 10 years ago. So a couple of groups have finally actually figured out how you can generalize this problem to a situation where both of the planetary bodies are massive, so you have to account for both masses. And interestingly, they showed that you can actually now, after a lot of complicated transformations, you can actually show that you can reduce those two resonant angles that I mentioned for first order resonance into a single resonant angle. So it's not as something very complicated, you can write it down easily, but you can show that you can actually reduce the problem to just a single resonant angle. And then there's a condition for this, there's some parameter called delta, which you can calculate for a particular configuration. And if that delta parameter is bigger than this number, then you can show that in fact there is a separatrix in the Hamiltonian of that problem that separates the resonant part from the non-resonant part. And so that's illustrated in these diagrams here for different values of delta. That when delta again is larger than that critical number, then you have this separatrix, which is this region, this curve here, separating the resonant region from the non-resonant region. So now you can actually, in modern times, you can now actually try to apply this when you have an observed system to see, if your system is actually in the resonance or not in the resonance by using this measure. So going back to the story of TJ76, when we first worked on this system back in 2002, that was soon after the first two planets were discovered, with orbiting periods of 30 days and 60 days. This is a system, other than resonance, is an unusual system because the star that they were observing is actually a low-mass star, so it's only about 1/4 the mass of the Sun. But these are two Jupiter-mass planets. And we now know that, in fact, it's not so common to find Jupiter-mass planets around low-mass stars. So this is already on top of the resonance. That's actually another interesting fact about the system. I showed you this radial velocity curve before. You can see that, so there are the 30-day and 60-day signal, which are overlapping with each other. But also, very importantly, you see that there's this overall big variation with periods of about 3,200 days or something like that. And that is, in fact, turned out to be due to the gravitational interaction between these two planets because they're in a resonance. And so the combination that you have two giant planets going around a low-mass star, the fact that they're in resonance, means that they actually have very strong dynamical interaction. And that actually is clearly something you can see in the radial velocity curve. And that actually, if you might remember, without that effect, we wouldn't be able to predict the degeneracy in sine line. But now we actually know we can measure the inclination of the orbits in this system. So for this, just starting with these two giant planets, again, remember in the old way of writing this, you have these two resonant angles. And as I said, both of these turn out to be vibrating around 0 degree. And what that translated to is the fact that these orbits are aligned relative to each other. This is again not what you would expect. If you do the lowest order analysis of this problem, you would have expected, as we have in the IO Europa configuration, that the two orbits should be anti-aligned. And this turns out to be, has to do with the fact that the eccentricity of the two orbits are non-trivial. They're actually quite large. One of the planets has an eccentricity of around 0.3. And they are large enough that the lowest order analysis doesn't apply. And so you have to start thinking about higher order effects in eccentricity. And then it turns out for this particular configuration, you would have in fact expected zero degree, which is a line orbit. We now know that there could be many other types of alignment, but we haven't actually discovered many of them. I've been hoping that we would discover some, but actually most of the ones I know of are in fact in this aligned configuration for the exoplanets. Now the animation here actually shows you the actual precession rate of these two orbits. Okay, so they go around 30 days, 60 days. And this is the two orbits are on average aligned, and they are actually precessing in a retrograde direction compared to the orbital motion. And this rate here has a period of about 3,200 days. So this is the actual precession. I didn't speed up anything. This is the actual precession rate of these two orbits. And it's because of that you can see very clearly the signal in the radial velocity curve, which has the long period of about 3,200 days, which is due to the precession of the orbits. I have to say that there are not many examples that nice. Actually, I think this is still the only example where you can really clearly see the effects of the interaction between the two planets. In most other cases that I know of, the effects of any dynamical interactions tend to be really weak, and you really have to do detailed modeling to even see that there is that signal here. Okay, so this is back in 2002 when I wrote that paper with Stan. Since then, as I mentioned, we now know that there are two more planets in this system. There is a really close orbit planet with a period of only about 2 days of about 7 Earth masses. So that one is not that interesting for this problem. But the more interesting one is that then later, there's this fourth planet with about 15 Earth masses, so that's about Uranus' Neptune mass, at orbit of 124 days. So the other two, remember, are 30 days, 60 days. This one is 124 days. And it turns out that, in fact, they are in the Laplace resonance with the orbital periods of 1 to 2 to 4. And so this is really now analogous to the Laplace resonance of the Galilean satellites in our own solar system. There has been some analysis to show that the radial velocity signal for that fourth planet is still actually not very strong. It's a relatively low mass planet out of 124 days. So the data, I think, is still, at least up to now, the analysis, we are still not entirely sure the dynamics of the Laplace resonance. But one of the interesting suggestions was that the three-body resonance might be, in fact, chaotic. So the Laplace resonance for the Galilean satellite is perfectly regular, but in this particular problem, it might be actually chaotic. And one of the things that I still hope to do in the next few years is to really go back and look at the system and try to figure out, in fact, if this resonance is actually chaotic. And one of the reasons this is something we can now do is that there's tons of data on this system. It's probably one of the systems with the most radial velocity data ever collected. So starting from the earliest data back in like 1990 something up to now, so this is the entire data train, lots and lots of different telescopes, including telescopes that are better than the original data with precision, better than the current data, previous data. And again, you can now see that there's been at least 2.5 periods of that precession. So I'm hoping that if we really, but this is really challenging to analyze. You have 10 decades of data, but the shortest orbital period is 2 days, so you can imagine this is really bad if you try to do fitting. So it's a non-trivial problem, it would be interesting to be able to tell if that free body resonance is actually chaotic or not, among other things. Now, other than system like this, I don't have a chance to tell you about some of the other systems that we know are really clearly in resonance, like as I listed earlier. But there are, as I mentioned, there are also systems that are near but turn out to be not actually in resonance. So I mentioned a couple of these to you. Both of these I was involved in, and these are actually both discovered by the TESS survey. And so these are both, I think they are both, in both cases, actually going around stars of about 0.8 solar masses. In the first case here, 2202, TOI 2202, there's the transit only discovered one of the planets, but it showed very significant variation of the transit timing, something called transit timing variation, which means that there's a second planet there perturbing its orbit. And there's then subsequently follow-up radial velocity observations. And by combining the transit and the radial velocity signal, we can show that not just the period ratio is a few percent off from exactly 2 to 1. As I'll show you also, you can then show that in fact it's actually not in resonance. And this is another one that's kind of similar. In this case, actually, I think this transit is observed for both planets. And there's, again, combined with radial velocity data, you can show that the period ratio here is slightly even larger, about 2.12. So based on that theory that I mentioned earlier, that you can now transform this problem into a single resonant angle with this parameter delta to tell you whether you're near or outside of resonance, you can now actually put different observed system on this diagram to see if it's actually in resonance or not. And these two particular systems here is actually the part of the parameter space that are clearly outside of resonance. So there are actually quite a number of systems with period ratios which are close enough to being within a few percent of being in resonance, but they're actually not in resonance. So that also, I guess I mentioned earlier, it poses a problem of why are there these systems that are very close to resonance but not in resonance. Okay, so another thing that I mentioned a few slides back is the fact that the first order resonances like 2 to 1, 3 to 2, 4 to 3, those are the lowest order resonances that are the strongest, and we expect most pairs to be trapped in those resonances. But it turns out there are now some really weird high order resonances. So I'll mention a couple of these which I actually was involved in. One of these is actually a system with a 6 to 1 resonance. So that means the period ratio are near 6 to 1 for these two objects. That's a really high order resonance. It's very surprising. You could even have anything actually in that resonance. This system was so I've been involved with a group from Heidelberg that has been doing a lot of radial velocity observation, including observation of giant stars. So this was from a survey that they conducted, one of the stars in their survey. So this star has a mass of about 2.7 solar mass. They had hundreds of, 150s radial velocity measurements. There was another Japanese group that actually has also been doing giant star survey, and they also have data for this system. And this is the radial velocity curve. Very nice. Nice period. You can see the very nice period for both. And we now actually have more data, still showing the same variation. And if you fit the data, you find that the masses of the planets, well, quote-unquote planets, actually are, the minimum masses would be about 22 and 25 Jupiter mass, which means that they're actually brown dwarfs, not planets. The orbital periods are almost exactly 6 to 1. And if you analyze dynamics, so if you do analysis of the dynamics and also not just the best fit, but the ensemble of possible fits, what we find is that all the possible configurations actually have all of the 6 resonant angles vibrating around 0 degree. So we are very sure that this system really is in a 6 to 1 resonance. And so there are a number of interesting implications about this. I'll mention this a little bit later about, again, this is a system in very high order resonance involving two brown dwarfs. A second system is actually in a 5-to-1 resonance. So this is a system that my current PhD student, Ying Yi, has been working on, also including Sabina Riefert and Shimon Trifonov. This is actually a main sequence stars around 1 solar mass, originally reported by the Swiss group using Corelli radial velocity data. And from that, we know that the period ratio is close to 5-to-1. What we've been doing is that, so a couple of things. One is that if you, again, take the radial velocity and try to fit that with two objects, you find that the inner object has a mass, minimum mass about 17 Jupiter mass, so again, that should be a brown dwarf on a fairly eccentric orbit, about 0.43. The outer object would be about a couple of Jupiter mass, and the period ratio, again, is close to 5-to-1. So one of the reasons why I got interested in this system was that there was a paper a few years ago claiming that from HST fine diamond sensor astrometric measurements, that they deduced that the inclination of both of the objects are very low, around 10 degrees. And then if that's really true, then if you divide by sine line, you find that the mass of these two objects are now actually the inner object would be a low mass star, and the outer object would be a brown dwarf, which is, again, really weird. So the first thing that we want to know is whether this measurement really is correct, that the inclination is that small. And it turns out probably not. So we've done analysis using both the Gaia DR3, what's called an astrometric jitter from the Gaia astrometric satellite, and also the difference in proper motion between Hipparcos and Gaia. Both of these actually allow you to constrain the inclination of the system. And we came up with a measurement of around 51 degrees. So much larger than the result from Bennett and Harrison, and less. So with that measurement, then these two objects would remain, one being a brown dwarf, the other one a giant planet. The other thing that we also are analyzing is the fact that there's now actually more data, especially from the HARPS spectrograph. And so we've been actually trying to do dynamical fits of the radial velocity data to see what we can find out about the resonant configuration. And so far, I think all the analysis seems to indicate that unlike that 6-to-1 system where all the resonant angles are vibrating, in this case, it looks like it's usually just one of these resonant angles is vibrating. But I think that in almost all of the samples in our analysis have this behavior. So most likely it's real that there's a 5-to-1 resonance, but it's not as neat, as clean as that 6-to-1 system. Okay. So lastly, I want to say something about how we think these resonances form. And there are a couple of important things. One is that as we now know from all the things that we have, all the planets that we have observed for exosolar planets, many of the behaviors, like these on Jupiter, tells us that in fact planets have migrated in their orbits during their formation. And the migration most likely is caused by interactions, at least for the giant planets and even for some of the low mass planets. They most likely migrated due to interactions with the gas in the protoplanetary disk, so planets form in protoplanetary disk, and through gravitational interactions with the gas, like illustrated here, we can actually generate spiral waves inside the disk, which then there's transfer of angular momentum, which can then cause the planet to move. In a system where you have multiple planets, then it could be that the two planets are actually moving in such a way that the orbital periods are converging to a simple ratio. So you could have started, for example, say, with ratio of 2.77, and if they move in such a way that they're converging on each other towards a lower number, then by the time they reach, say, 2, then that's a strongly resonant interaction, and in fact it's possible then for the planets to be trapped in that 2-to-1 resonance through this convergent migration process. So that was actually already known in the context of satellites in our own solar system, but in that case the orbital motion is actually caused by tidal expansion of the orbits. But in this case, we were talking about planets moving in the protoplanetary disk. And in the case of giant planets, most likely that they're moving inward. So one of the things that we did in that 2002 paper was to show that, in fact, you can actually deduce very strong constraints about the properties of the interaction with the disk from that observed system GGA76. And so we first of all showed that it is actually relatively easy to get captured into that 2-to-1 resonance with both angles vibrating about 0 degree. But what we also showed was that if all you have is migration and there's nothing going on trying to dam the eccentricity of the orbits, then it turns out that once the two planets are trapped in resonance, their orbital eccentricity would then actually go up very quickly and very quickly exceed the observed values. So that we argue that that means that there must be some sort of eccentricity damming process with that disk interaction to produce this observed resonant pair. And then by doing different calculations with different amount of eccentricity damping, then we deduce that depending on the particular way you do the migration, that the eccentricity damping rate compared to the migration rate has to be at least faster by a factor of 10 for you to actually reach eccentricity that look like the observed system. So that is actually a very strong constraint on what's going on in the disk during that migration process. In a subsequent paper that we wrote with Willie Clyde and Noel Murray, in fact, I think this started during one of the programs here at KITP, so Willie was an expert in hydrodynamic simulation of this, and we were doing some simulation for this particular system. And we were never able to get enough eccentricity damping in these simulations to produce the observed system. So we thought that there was still a problem with the model. But later, a few years later, and now I think we know that if you have, one of the problems has to do with how you actually treat what's going on in the inner disk, inside the pair. If you do it carefully enough, it turns out that there is actually sufficient eccentricity damping in the planet-disk interaction, and it is possible to then actually explain this system with including the eccentricity of the orbits through this planet-disk interaction migration and damping of eccentricity from the planet-disk interaction. Now, so then you ask yourself, what do you do about these high-order resonances, 5-to-1, 6-to-1 resonance? So as I said, if you remember, the 6-to-1 system actually involved 2 brown dwarfs. They're in the 6-to-1 resonance. So if the 6-to-1 resonance come from also a migration process, then you already can say something really interesting. These are 2 brown dwarfs which probably form in the disk so that they can migrate. And that's not what usually people think about when they think about brown dwarf formation. And then the next question is, how do you actually get them into a 6-to-1 resonance? Because it's a very high order resonance. The resonance interaction is very weak. And it turns out that we are able to have simulations where you can actually get these 2 objects into a 6-to-1 resonance. And it has to do with the fact that these are both relatively big bodies. They're both brown dwarfs, so the interaction was stronger. But also that it will still require really slow migration. And the orbits of the 2 brown dwarfs starting with relatively large eccentricities. And if you can satisfy slow conditions, then it is actually possible to put these 2 objects into a 6-to-1 resonance through migration in the disk. And again, this is still work kind of in progress, particularly with my student Minyi. Now, the last thing I want to say is actually about these resonant chains. So remember that other than these pairs of planets in resonance, we now have these resonant chains with up to something like 5 planets, 5 planets that are in the chain of resonances. So how do you form those? And in particular, many of those actually involve planets which are relatively low in mass, not the Jupiter-sized planets. You might be talking about the super-Earths or even Earth-sized planets. So a lot of the simulations that I have come across about forming the resonant chains are similar to the type of simulation that I was doing with Stan. It's very simple migration calculation. In particular, you just force the outermost planet to move inward, and then that almost guarantees that you can form some sort of resonant chain. But that's not really realistic. And the reason is that in the case of these low-mass planets, they are doing what's called a type 1 migration. So all the planets are moving. They undergo what's called type 1 migration. And the rate of migration depends on the mass of the planet and also the properties of the disk, including the slope of the temperature and surface, of the surface density and the temperature in the disk. And also, very interestingly, the migration can, in this limit, actually be both inward or outward, depending on the disk parameters and the disk and the time mass. So what I did with a student a couple of years ago was to ask the question of what are the conditions. So even forget about how you form the resonant chain. If the chain formed that when the disk was still around, so all the planets are still trying to move due to type of migration, what would be the conditions for actually maintaining that resonant chain? Because to maintain the resonant chain, all the components in that chain have to still be converging on each other in migration. They can't be divergent. Once, if they're trying to migrate in a divergent direction relative to each other, then you would break the resonant chain. So what we did was to think about the conditions that are needed. So an example here is if you have a 4-planet chain, right? Then you can think about the combinations. You can think about it as 2 pairs that are log in resonance, and the outer pair if they're both moving inward, the outer pair has to be moving faster than the inner pair, so that these 2 are still converging on each other to maintain resonance. Then the other combination would be 1 and 3. Right, and if you think about 4 in terms of 1 and 3, this triplet has to be moving inward faster than that one moving in. And then if you're doing the opposite, and then you can also have 3 and 1, so this outermost one has to be moving in faster than that triplet in the triplet. So this is if they're all moving inward. You then have all these reverse if you're thinking outward migration. And the nice thing about this analysis is that because the migration rate in the simple case can be written down analytically, you can actually write this down analytically also in terms of the criteria needed to maintain a resonance. So this is an example here showing you the capital 223, which has these 4 planets in this 8262423 resonance. So for each of the combinations, you can ask what disk parameters, so alpha and beta, are related to the logarithmic pressure gradient of the density profile and temperature profile of the disk. And the bottom line is that it turns out there are if you think about all the combinations and combine them, you find that there are no conditions for convergent inward migration to maintain the resonance. There are some parameter space for convergent outward migration, but this is problematic, not just because of the parameter of the disk that needed to do that, but also the innermost planet is already a 7-day period, and it would be really weird that you're actually having the innermost planet starting even closer in, and then it's moving outward. So this is not very realistic. And we did this for a few other systems, like the one shown here, and the same story, that there are no convergent conditions for convergent inward migration. And so there's a problem. How did we actually then form these resonant chains? The idea that we suggested was that if you look at the overall periods of these resonant chains, the innermost planet turned out to be usually very close to the star. And the idea would be then that one possible way you form these resonant chains would be that the innermost planet, they're all moving. The innermost planet move in, The disks usually have some sort of inner edge for some distance from the star. And because of that inner edge, the planet can actually stop moving if it's at the right location. Then the torque would actually, from the planet-disk interaction, would be 0. So then it stopped moving. These outer planets are still moving in. And so then naturally, that when that next planet comes in, it's a convergent migration. They can get long in resonance, and the third planet can come in, get long in resonance again. So that's one of the ways that we think these planets actually, how they ended up in a resonant chain. And we actually argue from the data that you can see some evidence for this. So if you have some simple estimate about where you think that inner edge should be for the disk, it should be something that actually depends on the mass of the star. And so this is a plot of where we think these innermost planets in resonant chains are compared to random sample of non-resonant systems. And the interesting thing is that they all have fairly close in, or as I mentioned, the innermost planet turned out to be in all these resonant chains, have very close in orbits, and they have some scaling with stellar mass, with big range, that actually could be consistent with the fact that the innermost planet actually stopped near the inner edge of the disk. Okay, so let me stop here. Maybe I can just put up the summary. All right. Thank you.
Got time for a few questions? Phil?
Great talk. I have a question about the depth of resonance and perturbations that might pull it out of resonance. We looked at any cases where there could be a case either from gas anomalies within the host or dust anomalies, or weather effects could occur in the system. Stellar evolution, for example, for near planets that are in a very tight orbit with a star could cause that to go out of resonance.
So there are definitely different things that can cause a pair to go out of resonance. As I think mentioned very early on in my talk, I was talking about our own solar system. Right now we don't have any resonances, but there are lots of models nowadays which propose that early on the planets, especially the giant planets in our solar system, was actually in a set of resonances. And what break that resonance was the interaction with the leftover planetesimals in the quantum belt, basically. So over time, the scattering was sufficient to slightly push Jupiter and Saturn apart from each other. And once they do that, then because Jupiter and Saturn are the largest planet, then once they start moving away from each other, then all hell broke loose and the whole system became unstable. So that's one way that you have leftover interaction with leftover material. In a disk, there could be a lot of turbulence going on, and that's actually one of the ideas I mentioned in the GJ706 system, that the free body Laplace mechanisms could be chaotic. And that has been, so if it really is chaotic, one possibility is that when that outermost planet came in, because it's relatively low mass, it was actually perturbed by turbulence in the disk. And so then it didn't get locked perfectly into resonance, but rather ended up in a chaotic situation. But because of that, you can imagine there could be a situation where, in fact, it didn't actually end up in resonance. So finding these near resonant pair and also the chaotic systems could actually provide some constraints on the turbulence in the disk.
It was a great talk. Thank you so much. I'm an astronomer, but I know very little about dynamics. So I'm just wondering if you take a step back. It seems like there are really interesting, discoveries here, but there are still handfuls of these systems. So overall, for someone not working on dynamics, should I walk away with a picture that planetary systems and mean motion resonances are overall extremely rare, but it seems as if they can teach you really interesting things about migratory processes. And what is the message, I guess, for the overall rarity of the systems compared to non-resonant systems?
Well, that's actually one of the kind of central problem right now about a lot of multi-planet system. So there's actually an interesting paper that came out a couple of years ago looking at the fraction of resonant chains as a function of age of the systems. And the claim, but very, very low statistics, there are only a handful of very young systems, was that I think like almost all the systems that were young were actually near resonant chain or maybe even resonant chain. And then the fraction was going down as a function of age. So if that's really true, it is telling us something about the possibility that in fact there were more systems that were in or near resonances at the beginning, but through different processes like dynamical instabilities, that they had gone out of resonance over the age of the system. And as you saw in that one of the earlier plots, that most of the systems we see now, the old ones, are not in resonance, but there are some excesses near resonances. So I think the combination, it will be really important to find more, just find more multi-planet system among the, as a function of for the younger systems.
Yeah.
I think that's going to be really important.
Max?
Speaking of younger systems, if I recall correctly, the HR 8799 direct range system is at or near resonance,
Yeah.
maybe with all 4 planets.
So the claim, I think it's pretty clear at least 2 of them have to be,
Yeah.
and maybe 3 of them are also in the last resonance.
Yeah. And my question was just kind of generally, have you looked at that system?
No, I haven't looked at that system much, but that system, as you know, is a very different one because the fact that it can be found by imaging means that it's really the planets are very far away.
Mhm.
And most likely, I think the scenario I've seen involve the fact that they're actually moving outward rather than inward. Otherwise, it would be just the formation already is a problem, and then most likely they have to move outward rather than inward to form if they really are in the resonance. But any sort of migration to cause the period to be converging. So in our own solar system, the satellites are all moving outward right now because of tides. And one of the classic explanations of why there are so many resonances in the satellite system is because, again, this differential outward migration due to tides.
Well, I guess in a typical binary system, there you got two bodies that are the same mass, and they're always pretty much always going to be one to one, right?
Pretty much what?
I mean, you did mention the dwarf system where the masses were about the same, but yet they were in some sort of resonance. But normally in a binary system, it's just going to be one to one, and they're going to work with the same masses. They're going to have the same rotational velocity.
For the binary companion, but I guess the context is actually, other than the binary, having something else in that system. And is it actually in resonance with the binary? And well, there are not that many planets. We haven't found that many planets around binary star system. But it has its own set of challenge because just having stable orbits around binary stars are not trivial. So that's a different set. There's an entire other set of dynamical problems involved in binary planets and binary star systems.